In this video, I will solve a concentrated stripping problem using Microsoft Excel. The problem statement, if you're interested, is in the upper left-hand side of this Excel spreadsheet. You may now pause the video and read the problem statement if you're unfamiliar. I've summarized the relevant details in this process flow diagram. The flow rate of water in is 20 moles per minute, and it contains 20 mole percent of solute, which is why we have to take the concentrated approach when solving this absorption problem. I've also input the values for parameters given in the problem statement here. Y out is one of the key variables that we'll need to find, and the problem statement is prompting us to find the number of stages and the outlet composition of the gas. I've alluded to this, that this is very subtly two separate problems. In this video, we'll cover only calculation of the number of stages you need, and I'll leave the calculation of outlet composition of the gas to another video. Now, if you're really good at material and energy balances, you may say, well, I can solve for the outlet composition of the gas from the outset using a material balance. And that is a valid approach. However, for reasons that we'll see in the next couple of videos, for a given number of stages, I may have inconsistency in what I get from an absorption stripping standpoint, what I get from a material balance standpoint. And that is why this is two separate problems. The question of how many stages do you need is a design problem, and the outlet composition of the gas is a predict type problem. So again, we'll see that in the next coming two videos. But anyway, because I have a concentrated system, I need to calculate my solute-free variables, which I have done here. Remember, L prime is the solute-free liquid flow rate, which is calculated by taking 1 minus the mole fraction of solute. In other words, that's the mole fraction that is just water. Or if it's 20% solute, that means the balance 80% is water, times the overall flow rate, 20. And the answer that I get when I do that calculation is 16. Similarly, for the solute-free vapor flow rate, it's 48 moles per minute times the mole fraction that is air. And in this case, since there is no solute in the incoming air, it's just 1 minus 0 or 1. Because L over V is a useful parameter to have handy, I've done that calculation here. Obviously, 16 over 48 is 1/3. And I can just reference this cell if I need it in the future. I've also converted the solute, the mole fractions of the solute to a solute-free basis. And the calculation there is the mole fraction divided by 1 minus the mole fraction. So 0.2 gets converted to 0.25. And I've also done that for big X out. And the formula there is little x out over 1 minus little x out. Just to plot the operating line and the equilibrium data, I've done that in this table below. So I've taken little x 0 to about 0.22. I know that I at least have to go to 0.2 because that is the whole range of concentration that I have. So you can drag that formula or select values of x all the way down. The values of y that are in equilibrium with that x is simply little x times the Henry's law constant. So in cell B34 is the Henry's law constant, and if I wanted to be very proper, I would divide by the pressure. But since the pressure is 1 atmosphere, that shouldn't change the calculation at all. Now, to plot the equilibrium data, I have to convert little x's to big X's. And again, that formula is little x over 1 minus little x. So I can do that in Excel just by adding another column and dragging that formula all the way down. Similarly, I can do the same for big Y. So it's little y over 1 minus little y. The operating line, the equation for the operating line for a stripper involves x out and y in, because we know what both of those values are. We know both x out and y in, and because y in is 0, I don't have to worry about it. So the formula is L prime over V prime times x of stage n minus x out. And I can copy and drag that formula all the way down. And if I plot my equilibrium data, which is the blue line, and my operating line, which is the orange line, I can get a sense for what these look like. Notice that the equilibrium line is very slightly curved. You may not be able to tell because I'm so far zoomed in, but if I were to plot the entire range of big X values and big Y values, you would see an obvious curve. If you ever get confused about which one is which, remember that the equilibrium data always passes through the origin to reflect the fact that it's linear in x and y. And if x is 0, then the y coordinate will also be 0. So how to answer how many stages I need? Remember, I'm going to stage step, and I'm going to start with the point on my operating line that I know. In other words, I know that the point 0.0204 and 0 is the bottom of the column, and I can start stepping my stage. In other words, this step would be stage 1, this step would be stage 2, stage 3, stage 4, and so on. And I have to figure out, where do I stop? So remember, I'm going to stop when I am on my operating line and my x coordinate has exceeded 0.25, which is big X in. So on my table here, notice I've numbered these stages a little bit differently than I typically do. I'm numbering them from bottom to top, which is against the typical convention that we use. But I'm doing that because I don't know what number stage n will be, because I'm starting at the bottom of the column, because I know both y in and x out. So y in is equal to 0. So I'm going to, in this cell, y from the bottom is going to be equal to y in, which is going to be 0. And x out, which is synonymous with x of n, or x from the bottom stage, is equals 0.0204. Now, how do I find y1? Remember that I have a relationship that says the vapor coming up from stage 1, or stage n, the bottom stage, must be in equilibrium with the liquid. However, big Y is not in equilibrium with big X. So therefore, what I need to do is have a column for little x and little y, such that I can convert, do the equilibrium relationship, and then convert back again. So if I take my equation for little x, I can flip it and invert it, and I can say that little x is big X divided by 1 plus big X. And I can convert big X back to little x. And this again makes sense because I know what my little x should have been. So that's a good check to make sure you're doing things correctly. Little y is in equilibrium with little x, so it is equal to h, I want to $sign that, divided by p, $signed again, times little x. And that will give me the y that is in equilibrium. The final step here is I have to convert back to big Y, so that is going to be equals little y divided by 1 minus little y. Okay, I can now drag all these formulas down because those are going to be the same for all. I'm going to go past what I think I need. X, that is in material balance with the y from the stage above. At this point, I'd like you to pause the video and see if you can predict what the formula for x2 should be. So this is you're going to use the operating line, and you're going to solve for x of n as a function of y of n plus 1. So go ahead and pause, and we'll come back and I'll show you what the value should be. All right, the equation for this operating line should be v prime over L prime times y of n plus 1 plus x out. So I'm going to say it is equal to y of n plus 1 divided by my slope cell, $sign, plus x out, which I can keep constant. And I'm going to copy that reference all the way down as well. All right, now as you can see, I'm starting to look for the stage at which my x value eclipses 0.25. And I see that happens in this cell, which corresponds to, well, I already have it here, so this would be my 9th stage, but that is going to be my top. So all of this I can delete. And on my graph, you see I already have the data points plotted here in the gray circles. So my first stage is going to be there. So my stage 1 is there, stage 2, stage 3, stage 4, stage 5, stage 6, stage 7, stage 8. And if I take one more step here, I am beyond my x coordinate, which is 0.25. Now notice I can solve for, I can see what the value of y coming out would be. So my big Y is 0.085 about, and if I convert that back to mole fraction space, I might say that Y out is equal to 7.82 mole fraction. However, if you do the material balance, you may find disagreement with that number. So again, this concludes the video about how to calculate just the number of stages. In the next video, we'll come back and I'll show you how to reconcile the two. In other words, how to make it such that the value that you calculate by material balances matches what you get by doing the stage step. Thanks for watching.